Okay, so here in example 3, it's dealing with a toy plane flying at a speed at an angle uh, east of north, right? At the same time, there's wind blowing fairly quickly at a speed and an angle east of north as well. Solving this problem won't be too different from previous examples, so if you would like, feel free to pause the video now, work it out, and then unpause later to watch how we do it. Okay? All right, so to start, just like all of your problems, you should always draw a picture. Right? For problems here in this chapter, the picture pretty much constitutes an axis and some arrows. So let's do that. Since we're only dealing with angles east of north and east of north, right? I only really need one quadrant. So there. I'll say due east like before is x and due north is y. Okay? And so we can draw these two vectors from the origin, right? Or starting from the origin, okay? We ultimately want to find the resultant velocity, right, of the wind pushing against the plane. So the plane's vector is about 50 kilometers per second at an angle 30 degrees east of north. The complement is 60 degrees north of east. So let's see here if I can do this correctly. So about 60 degrees, something like that, maybe? Okay, maybe. Let's say that's vector, again, we'll call it A. And then the wind is pushing on that plane at an angle of 20 degrees east of north as well. So if we want to draw another mini origin right there, east of north, 20 degrees, even smaller. So let's see. It's going up like that, right, at 30. So that's, I'm going to do it over here as well. B. Okay. That's kind of what we have here. Let's draw some components. In the x direction for component A, looks something like this, right? AX. For B, it's a little smaller, but I think you can still see it. BX, right there. In the Y direction, right, that's AY, and BY is very similar. And so if you can see, you might be able to, the addition of these is fairly straightforward. There won't be any negatives in this case. So we want to find the resultant, and I actually have drawn it over top of here. So let's say the resultant is going to be really close. It's going to be something like this. Something like that. Our vector equation, or the vector sentence, is simply A plus B. Okay, and then that in the x direction is equal to AX plus BX, right? And now is the time that you can put in minuses. So is AX negative? No, that's positive. So AX plus I hat. BX negative? Nope, also positive. Okay. Similarly for the Y direction, AY and BY, right? Again, we're keeping the same structure of our general vector statement, right? Just in X and just in Y. And so now breaking up these terms into magnitudes and directions, we have AY is the magnitude, the direction, positive Y. So that's plus J hat, and same thing for the BY. And so again, in previous examples, we have had to input a negative here, right? In this one, we don't actually have to. But if you do have to, if one of these components, 1, 2, 3, or 4, was in the negative direction, now would be the time to input it, right? Not over here, because this is still in vector form, right? But it's when you input it with the unit vector. Is it plus I hat or plus j hat, or is it negative I hat or j hat? Okay, that's the time to input it. And now is the time to input expressions or numbers, okay? So let's actually do that. Rx, let's do it, let's keep it the vector form, is ax. What's that? Well, it's the magnitude of a times, hey, we need an angle. I didn't write that down. That is 60 degrees, right? And that's 60 because it's 30 degrees east of north. So that means that was 30 and the other was 60. Okay. And just to clarify, cosine of 60 is the same thing as sine of 30, right? So I can put in cosine of 60 here, or I can put in sine of 30, whichever angle you want, right? It's up to you. It's your choice. Okay. I hat. Now for bx, bx was magnitude of b, which was 30. Whoops, I actually didn't put in a. That was 50. Sorry about that. 30, and then bx. Oh, this angle, what was this? Well, like before, 20 degrees east of north means that that angle there was 70. Okay, so cosine 70. And again, you could use sine of 20. And so if we add up that, if we evaluate the x component, we should get a value of 35.3. And the units here are kilometers per second, I hat. Right. For the y direction, we have ay, which was the magnitude of a. Again, it's 50. In the y direction, that's sine of 60 now. And just to be clear, sine of 60 is the same thing as cosine of 30. And then moving on with our last term, by. By here, sine of 70, because it's the opposite to that angle. And evaluating this for the y direction, we have 71. Wait. $71.5? Such that the magnitude overall, magnitude overall via the Pythagorean theorem that was 35.3 squared plus 71.5 squared, all this squared, gives us an overall magnitude of 79.7 kilometers per second. And then to find the angle, let's be a little specific here. That's the angle from the resultant r. Let's go down to the x-axis, right? That's the angle theta. Again, use inverse tangent because we know both opposite and adjacent of that. The opposite is the RY, 71.5, and the adjacent is the 35.3. That should give us roughly 63.7. And I think this makes sense, right? 63.7 is slightly larger than our original angle we have specified here. So just 3, almost 4 degrees more is what the wind creates. So the addition of that wind makes this plane head a little bit further in the y direction at a little bit faster rate, right? It also pushes it just a smidge in the negative x direction too. But anyway, that's example 3. Thanks for watching.